So now I'm working in McAfee, but previously I worked 4 years in Intel. Most of the research done and when we was in Intel, but nowadays we are in McAfee and having the same name of the team, and we continue to research this area, just a different company. Before I go to this area, I want to get some kind of introduction about why we need to think about BIOS, why this is important area, and in general firmware. So we have the kind of malware campaign like WannaCry, which is a main delivery method, and everything happen in ring 3 and ring 0. So kind of user mode and kernel, and really rare some malware go to some more privileged level like hypervisor level, SMM level, and so on. But nowadays, recent years, we saw more and more sophisticated attacks which is targeting low-level components of the platform, like firmware, like hard drive firmware, different other components of the platform, and different privileges level like SMM and virtualization level. So think about scenario like you're traveling and you don't have the locker in your hotel. You just leave your laptop. You never know what will happen with your laptop after, because someone can inject implants of the ear through physical access. As simple, this is a really simple method. It's also possible to inject implants in runtime, but that's more sophisticated and rely on vulnerabilities in your firmware. Another scenario is when you buy a laptop, you have no idea what exactly they are. You have no idea what firmware they are, what version of that firmware, how many firmwares you have, what components that firmware has, and so on. And this is giving us the idea of the problem of platform transparency. So you want to understand like what is inside your system. And for my definition of transparency is three things. First is, if there is any feature which can be disableable, the mechanism to disable and enable feature should be available, documented, and well known. So in case if you have like someone, like some vendor, without names, will have some extra feature in your laptop, like you want to disable this feature and you want to know that the features exist. Second is, you always want to have the read primitive. Like if you have the firmware, you always want to dump the firmware from two different methods, software and hardware. Read primitive is really important, and nowadays there's not too many firmwares have this read primitive. Because without read primitive, it's really hard to extract it. You need to find a way, you need to find the vulnerability. Like for example, if you're talking about SC firmware, to dump SC firmware, you need to find vulnerability in SC firmware, then you will dump it. So it's not the right way to do that. And third is, you need to match it with something. So after you have this read primitive, you dump the firmware, you want to match it, because without matching, it doesn't give you any idea about what this firmware is. And two interesting examples I want to give you. The one is, for my laptop, Lenovo T430, I've collected all of the BIOSes from the vendor side. And I assume that if I collected all of the BIOSes from the vendor side and I've parsed all of them and collected the hashes, I assume that if I run in my system matching to the binary which I have in my system, all of the binaries should be from the list. Because it's obvious, I just bought a laptop. Turns out when I ran it, I figured out that one module not in the list. I was kind of surprised because it's just one. It's not like 100, it's not kind of something which look like false positive. It's really just one module. So after a couple hours reverse engineering, I figure out that it is false positive, because there is this is version of the BIOS which has some different compilation, maybe options, and they generate a little bit different code. But I didn't find that BIOS in the vendor side. So I couldn't trust that binary if I not reverse engineer it, because I didn't find any source of this binary. It didn't exist. So that's kind of the state of the problem. And The solution, there is not really kind of silver bullet which you can just use it, run it, and say, okay, here is all input which BIOS handle, here is all components which BIOS has, you can verify it, you can check them, okay, there's like this amount of issue was fixed, and you don't have any kind of guarantee that all of this done or not done. There is no like kind of good mechanism. There's a couple mechanisms which can give you some answers, and that's kind of the main topic of my presentation. So I will go through the BIOS overview, then method how to statically and dynamically analyze BIOS, what kind of interface is accessible, how they're accessible, what kind of languages BIOS used to implement different component, and where is the parsing inside the BIOS, how much the code base to different component of the BIOS. Then I've explained a little bit how we can apply some different formal verification method to make some checks. Like, for example, in some of the BIOSes, in many BIOSes, there is SMI handlers, and in source code of the SMI handler, you have the comments which will tell you this function will handle untrusted input. And this is just comment, nothing else. So could be done more, like could be done some compilation plugin which will make some checks about who they call this function, how this function handle input, and so on. And a little bit about symbolic execution, because I think this really related to formal verification method, because it really represents that for the firmwares, formal verification is much more important than, for example, for huge software, because in the firmware area, you have a lot of code, but the traces, the size of the flow, which usually going through which are handling some specific input, there is much more smaller. Like if you compare, like for example, SMI handler, which is one of the runtime component of the BIOS, you have like always less than million instruction during entire flow from the beginning to the end. It's really less than any like even driver flow when you handle any IOCTL in any driver in Windows. So the amount of lines of code, there is a lot, but the amount of lines which is handling input and how they separate the flows makes us easier to have to implement verification method to that small flow. So small overview of the BIOS. So we have typically user mode, kernel, everything running. Everything can be running in bare metal, or hypervisor can be between hardware and the operation system. And SMM is the runtime part of the BIOS, which is living in the SMM mode and implement the SMI handlers, which make some management functionality of the platform. For example, if your cooler doesn't work in your motherboard, or is there any signal coming from some controller, in many cases it's going to the SMM code, and SMI handle it and get the information to the BIOS. Also, there's a software interface to the SMI handler. So operation system can call any SMI handler through the interface, through the I/O port B2. In general, BIOS is split into for two components. One is boot time component. Boot time component is everything which is running when you power on your system after reset vector instruction. So first instruction in the system is reset vector, and then after the reset vector, we have all of this complicated boot flow, which is big part of the BIOS. In that part of the BIOS, we also have the inputs, like it needs to parse the file system, it needs to parse the executable files, to load the bootloader, and so on. So that area has some vectors of attack. And the second part of the BIOS is runtime component. So runtime component is everything which is related to support some of the functionality which BIOS has to the operation system, including a runtime table, which is runtime UEFI table, which is implementing some functionality which you can trigger it, for example, read the write BIOS configuration, and so on. So what is different between BIOS and UEFI? So BIOS, like in the terminology of legacy BIOS, was implemented without any standards. It was implemented in assembler, and it was implemented through IDT table, through the handler of IDT table. So making any verification of that code was really, really complicated because it doesn't have any kind of formal, not formal, any kind of structure. Like Iverson was an assembler. You define the IDT table, then inside the handler you redefined it because you want to switch execution to some other flow, and so on and so forth. So the code base was really kind of not really structured and not really good for verification. Also, it uses the different proprietary mechanism to compress the BIOS. So in UEFI-based BIOS, the mechanism how to compress all of the code is defined as a standard. And all of the UEFI vendors use the same method, so you can unpack all of the BIOSes almost the same method. But in legacy, there was different method, and vendor used proprietary algorithms, so that was another really kind of interesting point to discuss. In legacy BIOS, also there was kind of fundamental problem with the protections and with the boot flow. So inside the boot flow, in the boot sequence, there was many points when the configuration should be done previously or it's too late and so on and so forth. There was no definition like what should be initialized at first, and if it's working, it's working. No one kind of touched it. And UEFI-based BIOS, there was completely different story. They make it standard. They put a lot of effort to standardize the boot flow, so you have the different phases, and the different phases should happen different things. And they kind of, there was more easy to validate them because there was all kind of part of the standard. Also, UEFI-based BIOS is almost C code. Assembler just small portion of that, maybe less than %. Almost all of the code is C code, implemented in a way that you have components which allow to reuse different components. All of the components has the similar method to call each other, to set callbacks. All of them set by similar compression methods and similar way how BIOS is built to the SPI image. So there is a list of things which is coming to the UEFI. I mentioned a couple. One of another important is the format of the executable components of the BIOS was standard PECOF format. Actually, there's two formats, PECOF and TE. For different phases, different format. There is just two loaders, which is loading different binaries, and that's it. All of the rest is standard. So they just need to implement correctly just two loaders, and after that, they can reuse it to entire phase to load all of the components inside the BIOS. So yeah, that's where is firmware living. So it's living between operation system and the hardware. And this is the different phases. That's standard picture for every UEFI presentation. So I want to be persistent. That's about UEFI, and that's the slide. So, but we have these phases, and what is important is that phases is pretty well defined, and in each phase should set some registers which is defined in that phase. Sometimes it was not that precise. So sometimes if the spec doesn't predict some of the right hardware configuration, it can be flipped. And for example, I know at least a couple registers which should be initialized here, but because BIOS vendor making some extra functionality and they want to have that interface unlocked until this phase. So it is kind of dangerous. It's not super critical, it's not security issue, but it's not kind of whatever is this phases was defined. And here is a lot of area when you can kind of try to apply the formal verification method when you, during compiler time, you can say, okay, if this is PI phase, and in PI phase, this set of registers should set. And if that set of registers is not set, then you just cannot build your BIOS. So even if the BIOS developer make a mistake and didn't log the register, he will figure out, okay, I cannot build my BIOS because I didn't set some registers. And that's because the standard is defining all of that, that's kind of one of the nice part of the UEFI. Another is important things for UEFI and also to apply verification method is configuration of the BIOS. Nowadays, configuration of the BIOS is pretty complex and stored in NVRAM in non-volatile storage inside the SPI. And the format of the every variable, UEFI variable, which is configuration of the BIOS, is defined. And every time when you kind of change the variable and read it again, you use the parson API. So if you have a chance to put some kind of misformatted variable inside your BIOS, you can use it to figure out read-write primitive to the BIOS. So that's really important point, and also really important point for verification is the property of the variable. So if the variable shouldn't be accessible after boot time, you can add this to the entire formal verification structure of the BIOS, and you will check, okay, now in this platform, for example, setup variable shouldn't be a runtime variable, because if setup variable is in runtime, then you can modify it, operating system can modify it and change configuration of the BIOS which shouldn't be accessible at runtime. And there is no kind of good mechanism which is verifying which variable should be runtime, which variable should be boot time. We have this in chipset, like simple check, like, okay, if you can read this variable, then mean it probably system vulnerable. But there is nothing integrated to the BIOS to check itself what kind of variable exposed to the runtime, and does the BIOS developer making mistakes. EDK2 has the reference implementation, so you can just download it and run any tests, make an investigation. Many bugs was found, by the way, in source code of the EDK, which was really good, and they was fixed before they come into the vendors, and the vendor didn't like kind of pull that bugs. So another important thing is because it's open source, you can also create all of these plugins and kind of apply it to entire source code of the EDK2, which with big probability will be applied to many vendors and many different places. Another really important point is that BIOS has multiple entry points. So I mentioned about a couple of them, but there's much more than a couple, and unfortunately they're all not the same. So they're all different and has different interfaces, and sometimes you don't have too much accesses to make a verification if you don't have, for example, some source code, for example, or something else. So one of the important interfaces is BIOS setting, which I already mentioned. So BIOS settings should be set properly during the boot, and any mistake in that boot time can be used to compromise a BIOS or OSNM. S3 boot script, there is kind of language inside the BIOS which is running when you come in from wake, when your system goes sleep and returning from the sleep. During this return, your system, instead of execute entire BIOS, execute just S3 boot script, which is kind of special language, which also restoring the configuration, which also should be restored properly with all of the security settings. SMI handlers, as I mentioned already, a runtime component really important to making sure that you have the SMI handlers properly handle input which is sent from the operation system. And here you can use kind of precondition, postcondition to check all of the things which you need to validate SMI handlers. Yeah, really quick about some of the tools which you can use to make some validation and maybe use it to build something with formal verification based on that tool. So chipsec tool has interfaces to has the method to access interfaces of the BIOS, which is accessible from the operation system. So chipsec has driver and user mode component, and the driver read a lot of interfaces to allow you to fingerprint your system, to talk to the BIOS, to trigger SMIs, to read configuration of the BIOS, to making sure that your configuration after S3 boot script is the same as before. Also has the interfaces to create the phasers, when you can define what the precondition and check if this condition is happening after, for example, for SMI handlers. When we found the bugs in SMI handlers, we just define, okay, we want this set of registers set before SMI handler, and we want to see this check after. And we run it for all of the handlers, and every time when we find that, okay, we got the changes, we check the changes. In many cases, we got the right primitive to SMM. So kind of BIOS doesn't have any validation to what address you supply as an input to the SMI handlers. That's the list of all interfaces accessible, so you can use all of them, depends on what exactly you want to dump. Right nowadays, chipsec support two different type of firmware, is the main firmware and option ROM, so you can dump these two type of firmware. In the future, we'll support definitely more firmwares as much as we can. If we figure out the read primitive to dump the firmware, we will add that to chipsec. A really good thing is a really good device which you can use to make a lot of interesting things in the BIOS area is Minomax board. That's the board which has open source BIOS. Entire BIOS is open source, except some of the components which proprietary for some vendors. But like kind of entire boot process with all of the stages is open, and you can implement your own component. You can enable TPM. You can implement SMI handlers. After that, you can run tests and verify your model. Also, you can use it to create the plugins to make a formal verification for some of the component like PE parser or compression mechanism or SMI handlers. Everything can be done there. We're using this platform to our training, which we're providing. So a really good, powerful platform to make a lot of research and tests in the BIOS area. Really fast about symbolic execution. So one of the main goals for us was to understand that SMI handlers is not vulnerable somehow automatically with good coverage. So we want to cover and see the passes and see, okay, this SMI handler has this amount of passes. We cover in kind of 90% of all of the passes, and we didn't find any integer overflow, any read pointer outside of write to the memory outside of SMRAM without checks and so on and so forth. So what we did basically is we dumped the SMRAM, so the memory of the SMM. How we did it, you can do it by two different things. One is using that Minomax board and experimenting there. Second is if you're having the vulnerability. So unfortunately, there is no silver bullet when you can dump SMM in any system. Unfortunately, SMM code is protected, and if you don't have vulnerability or you don't have experimental platform like Minomax, that will be tricky how you can dump it. But if you already done that everything else is pretty trivial. Then you get this binary, you load that binary in symbolic execution engine, you define where you want to start tracing and where you want to stop tracing and what kind of condition you're looking for. And then you just waiting until the symbolic execution engine will generate an amount of iteration and will give you the result of the coverage and what kind of condition it will have, like about integer overflow and reading and writing memory outside of the SMM and so on. So that's kind of what I mentioned, that you first dump, then you run it inside the QEMU and make that coverage. There is a separate paper about this tool published a year ago in the Usenix conference, so if someone interested, they can read about that. Yeah, some results. Conclusion. First of all, the firmware area has many different firmwares in any platform. It's not just one. Second is there is not all primitive is available. Third is if the primitive is available, there is no verification of that primitives, and there is no kind of golden images when you can compare. Third is even if you can compare that, you cannot verify all of the vulnerabilities because there is no easy way when you can by one click check in all of the conditions for all of the inputs because there is too much entry points, and some of them you can check, some of them you need to work a lot with reverse engineering and so on and so forth. So huge area. If you're interested about chipsec tool or XI tool or about BIOS itself, find me here or in Twitter, and thank you for your time.
So every time I start learning something about the BIOS, and unfortunately this is a race. The more you learn, the more new stuff gets added. And of course, your typical take is, oh my god, it's full of parsers. Rebecca Shapiro, a student of mine, is working on a project to disambiguate at least some of the parser's interactions with the inputs and outputs. Questions?
So we actually have a question from the internet. You were saying pretty early on in the talk that very little of the code of the BIOS is input handlers. How would you say the size of that compares between like original BIOS and UEFI?
That's an interesting question. I mean, it depends how you measure it. There is the semi handler itself. There is maybe I don't know hundreds of thousands, maybe less, compared to millions of entire source code DB. But there's also other parsers. So sometimes when you find a new vector, you find a new kind of source and new input, new entry point. I would say there's like kind of less than 10% of the code is handling the untrusted input, but I would say even less than 10. 10 is maximum, I would say.
Is that true for both BIOS and UEFI?
For UEFI, definitely. For legacy BIOS, it can be, depends, because legacy BIOS itself was smaller and that didn't have the infrastructure, and because of that, it may be more code to handle the input that in UEFI, because UEFI has infrastructure, different phases, and all of this. But interestingly, that every time when we discover new entry point, new vector, we figure out, okay, we find the new thing which you have a new parser like file system parser, P parser, like COM buffer parser, ICPI table parser, and so on and so forth. So as much as you investigate, I may know like 10 different inputs. Maybe there more exist, maybe 15, maybe even more. I didn't investigate, for example, TPM, how does inputs from TPM handle it, how does communication happen. Maybe there is something else there, and I didn't mention this in the slides. So I know what I covered, but I'm not sure that I know everything it's supposed to be covered. Go ahead, guys.
Okay. Yeah.
Anyone.
I find this terrifying in terms of the amount of an attack surface here. Does it really need to be this complicated just to do what the firmware on a PC does?
That's a really good question, awesome question. I'm asking this myself like 3 years in a row. So first of all, it's even more complicated than I explained it. I kind of make it super simple. I mean, for vendor perspective, definitely, because they want to have a lot of different features, a lot of different things. For our perspective as researchers, there is good example to make it simpler. For example, Core Boot. Core Boot has completely different story. And in Core Boot, there is one disadvantage. You cannot update it because they have they have read-only memory, and that read-only memory is protected by pin and by screwdriver. So if you want to update it, you need to unscrew the the thing, and then you can update it. So the one disadvantage is you cannot disupdate it. That part has programmability. But everything else is much more better because they use the read-only mechanism to validate the read-write part, and then they publish the algorithm how they make validation. Because they have this read-only memory, they disable a lot of features which is not necessary to have, and then to simplify a code for really small amount of lines. But the point is that because it's not applicable for every case. So for example, someone needs TPM, someone needs some other features, and they force it to have the update mechanism. So if you have a lot of features, you won't update them. If you want to update them, you cannot have the same method as the core boot has. You want to have like all read-write memory, then you need to enable configuration, then you want to have a secure boot to verify the methods, and so on and so forth. So because they have that much features, they want to support all of that. It is the way how you can make it better, and vendors is working on that. For example, nowadays all of them running chipsec before releasing the platform. So nowadays when you buy the platform, they're definitely much more secure than they was previously. But they still have a lot of issues with validating, for example, SMI handler. Because the second tool which I mentioned is much more harder to apply. Chipsec you can just run by 3 command line in Linux, but Excite you need to kind of make really hard work to apply. So, and that one is not done by vendors. And because of that, you have issues there. I hope I answered the question.
But you make it sound like all of some of these interesting security features like secure boot and CPM and what have you increase the attack surface vastly.
Yeah.
Let's make it one question whether your net security has gone up or gone down.
Can you repeat the question?
Well, once you've added, in order to get all of these features, some of which are security features like TPM.
It's not just security feature. It's
secure boot and what have you. Though.
Yeah.
You increase the size of the attack surface. So have you gotten net increase in security or net decrease in security by?
I mean, again, it depends how you measure. It depends how it is implemented. I would say some of the features really good, but some of the feature increasing the attack surface. For example, when we discovered the configuration of the BIOS and VRAM and all of the variable, that was not security feature. It was kind of mechanism to store the configuration. But it was interesting how many issues was there. So some of the feature is more important for security perspective. Some of them added more attack surface. It's all not kind of linear. Yes.
There are many parsers that are required just to parse the firmware file system, the initial format of the image, because it's so much complicated. It's made of different layers with custom compression.
Chipsec has it for UEFI. For UEFI based BIOS, Chipsec has it. We tested in 14,000 different UEFI based BIOSes, working well. A couple different tools exist for legacy BIOS. It is much more complicated, but I would say it's not really interesting because from 2006 or 7 we already have UEFI based BIOSes. So if you're interested in an area before 2007, yeah, it is much more harder to find the good tools there. But after that, you use chipsec tools and you can parse any image, including image from your system or image from the vendor sites.
Yes, you have UEFI too, but my question would have been, did someone have a look at this kind of parsers inside the BIOS implementation?
That's really a good question.
These formats are so complex, it's impossible.
So Sergey 3 years ago wanted to look at that. I don't know, does he look at that or not?
Well,
Definitely some people was interested in that area.
yeah. Partly, of course, this is a call to action, as have been all of our 3 invited talks. There is a huge unexplored surface here, and we're just starting to understand what it is. And like I said, we started looking at what a loader is as an execution platform driven by its metadata, and specifically bootloaders. But of course, we're not looking at the UEFI. We're looking at much more modest platforms for now. Any more questions?
So you obviously you're focusing on kind of Intel BIOS and UEFI. How's it like mobile platforms?
Really good question. So First of all, yes, we started with the classical UEFI firmware, but now we extended it now option ROM we support. We definitely will support hard drive firmware. About mobile, we ported chipset to the ARM, although it's not public unfortunately yet, but it will be this year. And then you can use it in a phone. In phone, it's really interesting story. So in the Pixel, in Google Pixel, there's 16 different firmwares, and many of them is not documented and doesn't have read primitive. So you need to kind of make a lot of effort to understand how does it work and to understand what the interfaces is and how they protect it. I have interesting result. Unfortunately, because we are in process of information disclosure with the vendor, I can just say some firmware is easy to dump and easy to investigate. Some of them is much more harder to dump and harder to investigate. And definitely transparency problem is applicable there as well. Thank you, everyone.
Let's thank the speaker.